Hey everyone, thanks for coming along. Actually, full house here for the Netty talk. Awesome. So, my name is Nitschinger. For those who haven't been in my talk yesterday here, I work for Couchbase, doing all the Java stuff there, lots of reactive stuff, and also responsible for the networking parts on the client side, where we make heavy use of Netty, and this is how I got involved into the project. And so I'll share with you a few war stories and give you an introduction to how Netty works. Um, who has used Netty before? Oh, let me start. Who has heard about Netty? Okay, great. Who has used it? Two hands in production? No? Okay, good. That's fine, that's fine. So we'll see how it goes. Feel free to interrupt me anytime. I again, like yesterday, I have lots of code to share with you. If we get through the slides quickly, I'll give you some demos as well. So it should be fun. And everyone, so I think talking about JVM networking with Netty is just half the fun. So the obligatory, it's high performance, right? And this makes the talk even more interesting. Probably, I don't know. So this is the Netty logo. Not very fancy, but you'll probably recognize it at some point. But even more interesting, what is Netty actually? So Netty describes itself as an asynchronous and event-driven network application framework for rapid development of maintainable high-performance protocol servers and clients. Blah, 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 blah. Let's focus on the important parts. Asynchronous and event-driven are, at least in my opinion, and if you look at the companies who are using these technologies and also Netty, are the basic building blocks of building high scalable and performance servers and clients, right? You need to make them completely asynchronous and event-driven to make sure you optimize for performance and so forth. Very similar to what I talked to about yesterday on RX Java, and basically the same principles hold, but here we go more down the stack, more to the IO layer, basically, so taking it top down. And it also makes for maintainable high performance servers and clients. The reason I'm saying this is because it removes lots of the boilerplate code as we see, right? Net is using NIO under the covers, but you don't have to deal with NIO directly. You write your pipelines, you write no business logic, and Netty takes care of the rest, right? You don't have anything from it's high performance, but no one can maintain this stuff. So it should be maintainable. Now, the, the the basic principle for me is that I think it's simple, and simple is always relative. But compared to writing NIO code directly, I think you can objectively say that it's simple. If we talk about communication, we need to think about both half and full duplex communication, right? So classical half duplex communication is what you have in the classical request response cycle, right? The client sends a request to the server, like HTTP GET, then you get a response back from the server. Now, there's also full duplex communication. Think about like WebSockets or other binary protocols where each parties are basically on the same level and they exchange messages as they see fit, right? And Netty supports both of those aspects, because technically, if you support full duplex, half duplex is just a specialization of full duplex, right? But it is different, because if you look at things like Apache HTTP client, right? Those basic HTTP clients that you find on the web, they all focus on the request response model, and building full duplex servers is much harder, doing it efficiently at scale. So one of the basic concepts that you run into when using Netty is the concept of pipelines, right? So what on earth is a pipeline? Well, imagine you have your application talking to something on the network, let's say an HTTP application server or something. Now, what you do is you need to take your message of some sort and then send it down to the network. And you do this by creating a pipeline of handlers, right? And the pipeline basically takes all your handlers and stuffs them into basically channels, right? I mean, channel is an overloaded term, but think of it like pipes, right? So where let's say you send a message to the server, it goes into the pipeline here, and then it goes through the handlers, and then on the other way, when you decode, it goes basically back up, right? So that's the idea of a pipeline, and we'll see um, how efficient it is, and also how practical, because the pipeline is not static. You can add and remove handlers from your pipeline dynamically, which is actually pretty cool. Now, taking it more from a flow perspective, you basically when you go downstream, you have your encoders. So you take a message, you encode them, and eventually you'll get a byte buffer here. And then on the other way back, when you get a response from the server, right, you basically pass your messages through the decoder pipeline, and then it eventually the business logic or your message for your business logic pops out at the very top, and then you do something with it, right? So very basic concept, but also very powerful because it really abstracts the whole encoding and decoding part that needs to go on to go from your business logic, your business messages, down to the basically byte buffer network layer, right? Which is the stuff you actually send over the network. And in Netty terms, you'll find encoder and decoder, but more generically, Netty calls those encoders outbound handlers and the decoders inbound handlers. Okay. Now, what happens if we need to group functionality? Consider you're implementing an HTTP client, an HTTP server. In every case, you need to encode requests or responses, and then you need to decode the counterparts, right? So you very often need encoding and decoding at the same time, and that way Netty has the concept of codecs, right? And the codec is nothing more than a basically it takes encoder and decoder into one codec, which you can put into a pipeline, and then you get both at the same time, right? So you can integrate an HTTP client codec, for example, which will take your HTTP request and do the encoding into a byte buffer downstream. And then on the other end of the pipeline, it will take the byte buffer and decode it into an HTTP response. And if you have a HTTP server codec, it will encode the response and decode the request, since you're basically doing it the other way around, right? Any questions so far on the basic concept of pipeline and those handlers? We'll talk about more about the handlers, but from the pipeline. Is that clear so far? Okay, great. Now, let's look at a concrete example. Imagine, or this is basically how we do it in the Couchbase Java SDK. So at the bottom here, you basically have your Couchbase server, right? And here is our Java SDK application. Of course, this is hidden to you as a user, but this is how we are doing it internally. So inside our pipeline, and this is for binary key value operations, right? So we are not doing HTTP or anything, but this is binary protocol stuff. Now, what do we have in our pipeline? At the very bottom, we have here what is called a binary memcache client codec, which is responsible for encoding binary memcache requests, turning them into byte buffers, and then sending them to the database. And when there is a response from the database, it takes those byte buffers and turns them into binary memcache responses. Okay, and then because Netty at this level here doesn't do any kind of aggregation. As the chunks arrive from the database or from any kind of server, it basically takes them and pushes them through the pipeline. So you can build fully chunk streaming based applications. But to make it easier for us here, we add what is called a binary memcache object aggregator. And what this does is basically it takes those chunks that arrive from the server and aggregates them into one pig request, right? So we aggregate those chunks, and then the next level here doesn't care what chunks basically arrived from the server. It just gets one big message, right? And that's the great idea of those pipelines, because the handlers in between only need to care about what messages they receive and what they send to others, right? They don't care about the rest of the pipeline. And then what we have in here, the next handler in the pipeline is called the key value auth handler. And what it does is it authenticates, but it has a very nice property that I'll talk in a bit. Now, and then we have the key value feature handler, which negotiates features with the server side, right? And then at the very top, we have a key value handler, which is a generic one that takes our business messages from the application, like, please perform a GET request, load me that document, right? And turns that into a request that this codec understands. Because very often your actual messages have much more stuff associated than what the actual protocol needs. Now, one cool thing about what you can do with pipelines, I said they're dynamic. Now, let's say we connect to the server, and everything gets added to the pipeline at this point. Now, if you look here, the key value auth handler, it's actually only needed during authentication. So what we do is, as soon as we have authenticated in the pipeline, we'll remove the auth handler from the pipeline, so that once basically we authenticated, there is no need for it anymore. So we can remove it and remove the overhead of letting the operations pass through another handler. And then similarly, we start to negotiate features with the server side. Like we send a hello command to the server, and the server tells us I'm supporting these features, and then on condition we enable them on the client side as well, right? But once this is done, there is no need for it as well. So during a steady state, we only end up with 3 handlers in our pipeline, and the other ones are just removed. So we don't pay the overhead for those anymore, right? And also you can add handlers on the fly. If you for example, need some specific functionality depending on stuff that you have negotiated in your pipeline, you can add them on the fly and then add them basically to your pipeline. So one other thing that I quickly want to mention here is that you need some way of course setting up the connections and everything. And in Netty, you do this by creating a bootstrap object. And the bootstrap object has many different options. It's basically a big builder where you pass in all kinds of stuff, which we cover a bit here in this talk. Here is an example, and all of the examples I'll show you are real examples taken from the Java SDK. So it's not something I made up. It's what's using in basically what's running in production out there, right? So you get a feeling of how to actually use this in a production scenario, not something code that I just came up with to make it simple. So the first thing we need to set is the remote address. So in this case, we are building a client. If you're building a server, you basically, instead of setting the remote address, you say on which port you want to listen and on which interfaces. Otherwise, it's very similar to. The next thing is you'll set a group. And what the group is think of it for now as like a thread pool. So Netty calls it an event loop group. And what it does, it basically, it creates one event loop. So let's say you create an event loop group of 5 threads, then it will create 5 event loops in the background and then multiplex all the incoming connections on top of those event loops, right? So it removes this one socket per thread model that doesn't scale, and by using explicit event loops and multiplexing sockets on top of those, you can get thousands of connections basically feeding into Netty and still getting a good performance, because what I recommend you to use is a pool size of not more than physical cores, because otherwise you get all kinds of weird effects where the CPU needs to schedule them and so forth. So make sure that your basically event pool size is really just the number of CPU cores. And the next thing is here we set a channel. You can ignore this for now, but you'll probably, if you create an NIO event loop group, you'll set this to NIO socket channel. So it's basically just a fixed param that you set. We'll see this as a small implication afterwards, but I'll come to that. And then you optionally, you can set all kinds of options. So here, for example, we set an allocator. In our case, we're using a pooled allocator. So we are reusing byte buffers and generating less garbage. We set TCP no delay on the TCP socket. And also we set socket connect timeout here, right? So you can set all kinds of network params here as well for each connection. But that's all fine, but where does the pipeline come into play, right? So what you do is you attach an initial handler, which is called a channel initializer. And here, you get access to the pipeline. So what you'll do is, once a connection is established, or once the channel is created, you get access to the pipeline, and then you get an initial opportunity to populate your pipeline. And in this case, what we'll do here in the Java code is they will say, if we have SSL enabled on our Java client, then we add the SSL handler to the pipeline. So Netty ships with SSL out of the box. So we can say if the user enabled SSL, then we add an SSL handler. Otherwise, we don't even need to add it to the pipeline, right? Then the next thing, if tracing is enabled on our logger, then we add a special logging handler into our pipeline that basically trace logs all the bytes that are coming over the network. So it's very verbose, but it's great for debugging, right? But we only need it if trace level is set. And then we call custom endpoint handlers here, because this part is generic in the SDK, and then for each different handler we add, for each different endpoint we add the handlers that we need. For example, here is the we've seen previously for the pipeline with the KV handlers. What we do first here, and I didn't put this on the other slide, is if a keep alive interval is configured on the environment, we add another handler that Netty provides, which is called the idle state handler. And what it does is, as long as traffic goes through, it doesn't do anything. But you can configure an interval here. And here we, for example, say after 2000 milliseconds, an event will be sent down the pipeline where you can react to, right? So for example, what we do there is, if no traffic is going on for 2 seconds, we'll send an HTTP head to a specific URI to make sure the connections don't get dropped. We had very weird cases in the past where firewalls would just blindly basically drop connections because nothing was going on. And then someone sent a request, and of course the connection broke at this point. To avoid that, we send regular heartbeats, and you can do that right in your native pipeline. You don't need special logic for that. Okay, so we do the keep alive, and now this is the equivalent of the slide from before, right? So we say pipeline at last, and there are many methods available to add your handlers at specific points in the pipeline, but here we just create them one after another. Here's our client codec, and you'll see it's basically top to bottom because they will always be appended to the end. First, we do our memcached client codec, then we have our aggregation, then we have our authentication handler, then our feature handler, and finally there is our key value handler that handles our actual business logic, right? Okay, enough about pipelines. Let's talk about handlers. Basically, they are workers, right? Our steel workers of Netty. In general, think about for a handler as a handler very generically, it receives events from the pipeline and it also emits events into the pipeline. And if you take that concept from a very generic point of view, a message is also just some kind of event, right? But there are many other events that you can also send and receive into your pipeline. Let's look at an example. So what you're seeing here is the feature handler that I talked about before, where we negotiate features with the server. This is how it's implemented. So the first thing we'll override in our handler is a method called channel active. And unsurprisingly, this event will be called as soon as the channel becomes active, right? And this is the point where we can actually do nice things. So in our case, we send, and the context, the channel handler context is something in Netty that gets passed around all the time. This is basically your context where you perform your operations on. So in this case here, we say write and flush, and then we send a hello request to the server. Now, why write and flush? Netty has a concept of, there's a difference between writing and flushing. If you write something into your pipeline, it gets written, it triggers down the event loop, but it's not actually sent to the socket. Only if you send a flush message, then all your previous writes will be sent to the socket. This means that you can do batching very efficiently, right? Because sometimes you just want to send chunks, and then at some point you want to flush, right? If you want to do both at the same time, you just call write and flush as a shorthand. All right. So what is this hello request that we are sending to the server? Now, the hello request here is a full binary memcache request, which is what our handler down the pipeline understands, because our handler at the very bottom needs to take this binary memcache request and turn it into a byte buffer and send it over the network. So here, our memcache request, basically the constructor says, okay, we need a key, we need some extras, right? It's protocol details. Here we are just creating this kind of message. So we set the key, and again, this is just protocol internals. But all you basically do is you create this message which your codec understands, you set some properties, and then you write and flush it down the pipeline, and then the write handler will pick it up and then send it to the server. And the cool thing is those encoders and decoders are typed. So the memcache request will only be picked up by a handler that actually understands this type of message. So you can have different handlers in your pipeline that react to different messages, and they won't step on each other's toes, basically, right? Now, okay, so we sent this message to the server. Now we also need to read the response. And for this, we override the channel read method here. And what we'll get, because we already had the decoder from the binary protocol in place, we're not getting some kind of arbitrary byte buffer, but we actually get the full binary memcache response. Why full? Right, we had the aggregator also in place that basically turned memcache response chunks and aggregated them into one full binary memcache response, right? But that's the beauty of the whole stack here. And what we do is we check on our response if it's a success, and then we basically do some business logic to pass out the features that are supported on the server side. And then we log, okay, we negotiated those supported features. And then we fire a user event. So Netty provides events like channel active, channel inactive, connected, all kinds of events that you can override and react to. But in addition to that, you can fire your own user events. So in our case here, we fire an event which we call server features enabled. With the features we found that we negotiated, we send it up the pipeline, and at the very top, one handler takes this information and then does some kind of business logic, decide, okay, we can't send this request, or we need to enable compression and so forth, right? So you can imagine, for example, you enable compression with the server side. The server tells you, oh, I'm supporting compression. And then here, you could even say, okay, if the server supports compression, I'm adding my compression handler to the pipeline, right? If it doesn't compression, I'm not adding it, right? So you can do all of this dynamically on the fly in a very convenient fashion, because even if you add compression here, your handlers at the other level have no idea that compression or SSL or whatever is enabled, right? They just work with your pipeline. Now, what handlers does Netty ship out of the box? There are many different handlers, right? You have, I would group them in categories, like there are byte-to-byte handlers where you take one byte stream and transform them into another byte stream. And then you have byte-to-message encoders and decoders that basically take a byte stream and turn them into some kind of message. And then you have message to byte and message to message handlers. And then there are more, a little more sophisticated handlers that are provided, but they are, I would say, building blocks, right? Especially if you're dealing with binary protocols or line feed protocols, they're very useful, as we'll see in a second. So, for example, you can have a handler that is based on a fixed length frame. If you know your protocol has, for example, 60 bytes per message, you can tell it, okay, every 60 bytes, grab them automatically out of the stream and send them basically up the pipeline. And there are others as well. You can have it delimiter based. This is very common if you have ASCII protocols where you terminate with a \n. You can set your delimiter to \n, and then Netty will handle all the nitty-gritty details of waiting until all the chunks arrive, until the \n comes along, and then send the message up the pipeline, right? And then on top of those handlers, we have codecs. And Netty ships with a lot of codecs, including HTTP2. So there is full HTTP2 support right now in Netty. Of course, HTTP, Memcache, that's the one I contributed and that you saw before. There is MQTT, Redis, SMTP, SSLs. There are all kinds of protocols, but adding your own is actually pretty straightforward. Let's look at an example. So I talked a little bit about our binary Memcache protocol. So this is a header that we use for our binary protocol, right? So you have some kind of magic byte and whatever. But the important part here is, at some part in our header, there is the total body length. And we need the total body length because the server is sending a response in chunks, and we need to know when we are done processing the whole thing, right? So what we could do is we could write our own handler that basically takes the chunks. It first waits until it gets 24 bytes because that's the total header size. And then once it has the 24 bytes, it parses it. It takes the body length, it takes the extras, and it takes the keys that would be attached down here. And then it would wait until those arrive, right? We could do all of that on our own. But thankfully, so, one other property I should mention. So the total body length includes the extras and the key, right? So this is the header, and then the total body follows, which is made up of all the extras and all the keys and the content, right? So imagine you are sending a GET request, say, give me all for this document, and you get back a JSON document of 100K or whatever. Then the key is, for example, foobar. Then you would have 6 characters for the key length, and then 100K for the total body length would be 100K and 6 bytes basically, right? And then you'd get all of this afterwards. Now we could deal with this on our own, but we could also use the length field-based frame decoder and say, okay, the first value here is just the maximum frame that it could basically take. But because our total body length is an integer field, we say, okay, it can be basically full integer range for the full body, even if it's unrealistic, because Couchbase only supports 20 megs of document body per document. And then the next argument here is basically tell Netty where it should start looking for the total body size, right? And here we have a constant which says body length offset. And if you look back here, well, our offset is basically 8, because we tell it skip the first 4 bytes 8 bytes and then start basically looking at the total body length. And because it's an integer, it's 4 bytes long, right? So it will automatically read the total body length of 4. And then we also need to tell it, okay, if it would now start reading the total body length, we would actually be screwed, because if you look back here, we have another 12 bytes of an opaque value and a compare and swap value that we need to take into account as well. Otherwise, we would not get the full data, right? So we also tell Netty, okay, please also add 12 bytes because those extra also take 12 bytes, and then add the full body length. And if we do this, what we'll get up the pipeline is a byte buffer of exactly the size of our message, right? So basically, Netty does the message parsing for us, and we get a byte buffer where we know we have the header and the content as part of it, and then we can do something with it, right? So it doesn't matter if you do lots of, I would say, high-level message-based encoding and decoding, or you really want to go down to the low level and only work with byte buffers, you can do both, right? All right. So that was a quick introduction to handlers pipelines, how easy it is to work with it, but it's also fast. So when I ported our Java SDK to Netty, I did some interesting examples. This is with batching enabled and so forth, but I easily got, this is one JVM and one couch per server, and I easily got it to 800,000 operations per second, right? It is, of course, you can't take these by any measurements for what you need, right? But I just wanted to emphasize is that if you work with Netty in a very efficient way, you can easily push hundreds of thousands of operations through this thing without too much hassle. Now, looking at some more sophisticated stuff. So Netflix, when it was a few years back, it was working off moving off Tomcat and making sure their streaming infrastructure, basically where you do all the like, you go to Netflix and you look for a movie and so forth. This all goes through an RX Java and RX Netty backend, because they have an RX Java Netty integration, which they call RX Netty. And they were benchmarking their current solution, Tomcat based, with Netty. And it doesn't, the actual numbers don't matter, right? But what I can tell you is they got significantly more throughput at lower latency, right? So here you can see basically, especially at the 99 percentiles and so forth, the Tomcat latency really shoots up, and Netty really allows you to go for low latency. And the throughput and latency mix is very important. Who has heard about the Tech and Power benchmarks? One? Okay. I expected more actually, because it's very often in the news and people always make a fuss about it. So what they do is basically they have a fixed set of operations they run against an API, and then lots of different implementations are there to implement it. Like, for example, here it does some plain text request response. And obviously here is Undertow, the HTTP server. I think it's under Wildfly, if I'm not mistaken. It ranks at 5.6 million operations per second. And then Netty here is in third at 4.9 million, right? And I only included Java here to get a fair comparison, because comparing with C and C++ doesn't really make sense, right? So you would think, oh, I should probably use Undertow because it's, I don't know, it's 500,000 operations faster for this use case. Why is Undertow so fast? And I would say not so fast, because the problem is, if you then look at the latency, you'll see Netty serves those 5 million operations at average latency at 76 milliseconds. And I really don't like averages, because they really completely screw your numbers. But if we compare averages and averages, okay, let's do it. But you see Netty at is ranked here at 1.5 seconds, right? So it achieves nearly the same throughput, but the latency is completely ballpark. And what you want in a real production benchmarking, you don't just throw everything you can at the system. What actually says, what is my acceptable latency, basically my upper latency, and then you increase throughput until you reach that latency, and then you basically know your numbers, right? But just adding more and more requests will, in the worst case, basically get you unacceptable latency, and those throughput numbers don't mean anything, right? But I just wanted to show you that even under high throughput, Netty allows you to really get a very low latency, which is very important in production systems. Now, why is that? Netty has this concept of event loops that I mentioned before and socket multiplexing. And more systems are doing it that way, of course, because it is very efficient. But it's not only the threading model it uses, but it's also very heavily GC optimized. So the team is going great length to reduce allocations as much as possible. They are using Unsafe in lots of places. I would have to tell you that's something that not everyone agrees with, right? There are many people that say, "Oh, never use Unsafe" and so forth. Netty uses Unsafe, but you can disable it if you want to. It does lots of object pooling with something that is very similar to what gmalloc does. So you get a byte buffer allocator and you need to release your object and so forth, right? It takes some time to get used to, and you can also disable the pooling if you're willing to treat more GC basically for ease of development. So that's one thing in that area. And then there is just in general lots of mechanical sympathy. So if you know Martin Thompson and what he's doing on high performance work, he basically coined the term on IT, and so it's just doing lots of stuff that works really well with the JVM and makes it very fast, right? And of course, there's always trade-offs, right? I wouldn't use Netty if you just want to do one HTTP call against some kind of server, right? There's other software out there. But if you want to write high-performance scalable server applications, then this is the way to go, because that really allows you to crank it up to 11. But there's more. Netty really goes the extra mile to a degree. Now, a few years back, so Norman Mauer, he's one of the maintainers of Netty. He's from Germany. He was thinking, okay, how can we? NIO is slow. It uses lots of synchronized inside the JDK, right? We can fix that. Well, how could we fix that? We could use JNI and talk to ePOL directly, right? So he started working on basically a native transport that basically circumvents NIO directly on Linux and basically talks directly to ePOL. And if you think about that, using ePOL over JNI scares a little bit. I don't think you're alone. But thankfully, the way it is packaged is very easy. So I hand-waved a little bit the event loop group and the socket thing up front on the bootstrap. And here is where this comes into play. So what you always define is an event loop group, and every event loop group type has a socket channel that you pass in there. And all you have to do on Linux, if you want to use ePOL instead of NIO, is instead of passing in an NIO event loop group and an NIO socket channel, you pass in an ePOL socket channel and an ePOL event loop group. That's all you have to do in Linux, and suddenly you get basically direct talking to ePOL, and you get even more performance out of the thing, right? So here's another example from the Java SDK. How do we implement that? Well, we say by default, we always default to NIO socket channel because it works everywhere on Mac, on Windows, on Linux. But the user can explicitly on our environment config, if the user passes in an ePOL event loop group, then we set the channel class to ePOL socket channel, right? That's all there is to it that you need to configure for even more performance out of there. We basically just support it out of the box, right? Another thing, the buffer pooling. So this is a little older. This is from 2013 when Twitter, who is also using Netty extensively, like Facebook and all these other companies, right? Google, Apple. They were basically benchmarking Netty 3 and Netty 4. Netty 3 doesn't have the buffer pooling, and Netty 4 does. And this was the period when they were looking at migrating to Netty 4 and looking at the buffer pooling and so forth. And there you can see basically the more you allocate, the longer it basically takes in GC cycles. And the cool thing is what you can see here, basically the buffer pooling, right? The yellow and the brown bars here are significantly lower. And it is a little bit expected, right? Because if you avoid GC, then you have lower GC pauses, right? And especially in high throughput systems, every byte buffer counts that you don't need to GC, right? And you can take this as low as possible, right? Of course, if you create your own business logic objects, then you need to allocate them. But I think we have some time. I can show you a demo where we basically stay at the byte buffer level and we avoid all kinds of allocations, right? We go at gigabit per second level, right? That's also totally possible with a plain JVM on your laptop. Where next? So after this whirlwind tour, now you're super happy about Netty. What are you going to do? So the first thing is, Norman always asks me that you should make him rich. You can buy his book on Netty in Action, which is great. I read it, I think, 2 times, and I mean, honestly, there is not super documentation about Netty out there, right? There is a wiki, but you very quickly, after the examples that are on the repository, you need to dig into the code. But this book really takes you from 0 to 100 on everything that you need to know about Netty. If you don't want to buy the book, or in addition to that, go to Netty.io. People always hanging around on Freenode. Yes, lots of people still use RC. There's a mailing list, Stack Overflow, and Netty uses GitHub to track issues. All right. So, any questions before we go into view demos? Because I think we have some time left. I try to breeze through a little bit further so we have more time for demos and questions. What do you mean? Okay. Okay.
Yes, please. Good. I just need to hear if there's audio here on the recording as well. Can you say something?
Test.
Okay. Well, you just continue and I'll manage. Maybe it will come
Okay.
without sound.
Test.
You
Test.
can hear you.
Okay. All right. Okay. So let's look at some code here. And what I'm going to show you is that I'm not going to show you the Java SDK directly because it's lots of code in there and you've seen some code already. What I'm going to show you instead is we built a new client that is called the DCP client. What it is basically do configuration management because you can imagine that if you have a multi-node cluster, nodes can come and go on the fly. So we need to get a way of basically knowing when a configuration change happens on the server side. So the server for us provides like an HTTP chunked feed where it sends us a new configuration every time it has one. So this is how we set up the HTTP pipeline. We create our pipeline here, and then on our init channel method, we only have two handlers. One is the HTTP client codec, which is provided by Netty, so we don't need to care about taking the byte buffers and parsing HTTP, right? Here we don't care that much about performance. We want to make sure it is basically, since it's a config side channel, as you see in a bit, the data channel only uses byte buffers. And then our next codec is our config handler. And how does the config handler look like? The config handler extends the simple channel inbound handler. And if you recall from before, inbound handlers are decoders, right? So messages arrive from the network, are passed through our client codec, and then our inbound handler gets a channel read event, and you do something with it. Now, if you recall, also previously I showed you our aggregator where we had the full HTTP response. There is also an HTTP aggregator which would take all the response and then return it to us. Now it turns out if the server returns an HTTP chunk stream and never ends, we can't wait until it's aggregated because it will never finish. So in this case, we need to handle the chunking on our own. So what we do is every time we get an HTTP content object, we call decode chunk, and this is the byte buffer chunk that arrives. Because what happens also is that in the HTTP codec here, it distinguishes between HTTP content and HTTP message, right? So you have your 200 OK response, and then the body follows, and it doesn't have to be clear text. So what we do here we don't care about the HTTP 200 because we know our stream is going on anyways. So every time we get content, we extract the content out of our HTTP content message, which is a byte buffer, right? We take the chunk, we turn it into a string, because we need to check if basically it ends with 4 \n. This is the convention of the server telling us, yep, the current config is over, right? And we could even do that on top of the byte buffer, but here it's easier if you do it on top of the string. And then if we are not finding the 4 \n, then we just store the chunk and wait until the full chunk arrives. If it does, here we're using some RxJava. We're basically using an observable to feed the config into our subscribers, right? Because this part really only cares about taking the config from the server and then feeding it somewhere else. And here you can really see the difference between handling business logic and handling network stuff. Here we really only care about this config that arrives. We don't care about what NIO does underneath and so forth, right? But it's still efficient and scalable. Now, also what we have to do is because we need to clear the buffers if we don't need them anymore, right? That's part of the byte buffer stuff here. And also, what you see here is we are overriding the channel active event, which Netty will trigger us if the channel is connected. Because at some point, we also need to send the HTTP request once, so we get the stream. So once we are connected to our socket, we create the full HTTP request, and then we send it basically down the pipeline. And the client codec downstream understands the full HTTP request, right? So we add an application JSON header here, and then we also add HTTP basic authentication because that's part of the protocol, and then we write the request. And then the response, again, would here be in our channel read decode, and that's all there is to it to actually parse and basically handle a JSON stream of configs. I don't show you the config handling because that's not related to Netty. Now, the actual pipeline where we do our data, and you probably recognize this. So here comes the length field based frame decoder into play, right? In our Java SDK, we use the memcached message that is part of the codec, basically, the memcached codec that's part of Netty. But here we really want to go low level. We don't want to allocate messages that we don't need. So we only use the length field-based frame decoder. That's an interesting word. And because it only operates on byte buffers, which are pooled, we are not actually allocating anything out of the pool, right? And then here our pipeline is again, we have our auth handler, which also will be removed once we authenticated. And then we have 2 other handlers that will also be removed. One does the DCP handshake, basically, not the TCP, but the DCP handshake with our server on the server protocol. And then we also negotiate features with the server side, right? So in the end, all we'll have is our length field-based frame decoder. If tracing is enabled, our logging handler, and our message handler, which will actually take the feed of changes and then publish them somewhere. Now, let's look at the message handler here. And this is where, and you can see it's actually not much code. It's like 50 lines of code, and this is really how it runs in production, right? So every time a new byte buffer comes along, and at this point, because we have the decoder in place, we know it's a full packet, right? We don't need to do any chunking. At this point, we know if the byte buffer is of a specific message type, and here we are using a flyweight pattern to not allocate any kinds of objects. So here you can see we're basically we are just basically really just operating on. If it's a data message, so it's either a mutation into our data callback, which is where the user attaches its business logic then. If it's a control message, then send it to the control callback, because this is where we do all the snapshot handling, because you can imagine in a distributed system with sequence numbers, you need to keep state. If you have a rebalance going on, if a failover, you need to roll back to a specific point in time. That's all handled in the control path. And then we also issue NOP requests against the server. So if you set this control flag up front, we do NOPs at a specific point in time to make sure the connection is alive, because the server has a property to say if this is negotiated and nothing gets sent for a specific period, it will just close the connections to make sure it gets cleaned up properly. So this is how we do all the messaging. And then so here you can see the data event handler and the control events. And then if we look at an example here, you'll recognize that these are our callbacks that we attach, right? So here's our control event handler, which gets we get the byte buffer, right? And even if we don't do anything with it, we need to release it, because otherwise it will leak out of the pool. We will not get basically put back into the pool. And here we're doing a little bit more with our data. In this example, what we do is we basically take we count all the changes that are coming in, right? There is a, let me show you a simple example. So here what we do is we say stream from the very beginning of the data that's in the server up until now, so what the current point in time. So we call this a backfill. And then what we do is we just count the number of documents that are currently in the system, and then we also aggregate the total size of the document. So this is just a very simple example. So we check if it's a mutation, we perform this. And very important, this operation here is handling on the event loops. So you're not allowed to do anything there that's blocking or costly, because that would swamp your event loops. But if you do it right, if you do it without, like if you use atomics, or if you need to do something costly here, you would put it into a queue and then consume it from a different thread to make sure that your event loops are basically running fine. So it's a very low-level abstraction here, but that's the cool thing, right? If you have powerful low-level abstractions, you can build your high-level abstractions on top of it. If we already would have all kinds of locking here, the performance would already be lost. And then here we just loop in the current thread, and we have our session state. That's all TCP rated. That's not very interesting for this Netty talk. And then we just print it out here. But the important part here is with this code that you've seen, basically with limited allocations, basically feeding the stuff through. In my benchmarks that I did, you can easily saturate gigabit networks with that. That's absolutely no issue, and the JVM is not breaking a sweat, right? So taking it from there and then building your abstractions on top of it is very powerful. And yeah, happy hacking on Netty if you want to build those kind of servers. And I'm happy to take any questions either now or later in the hallway if you have some other stuff you want to discuss. I think we are right on time. 2 more minutes for questions. Okay. Yes?
What Java versions do you support?
6. 6 up, yeah.
Form of asynchronous I/O that's being done, is that really real asynchronous or not just non-blocking?
It is asynchronous. So what happens is basically under the covers, of course, with NIO, you basically have your selectors, right? But what we do in more complicated examples here is, for example, when you write a message to your handler, what I'll do normally is, for example, I'll store a callback in my handler, and the handlers, what I didn't mention is the handlers, because they run in a single thread loop, they are also expected to always run in the same event loop, which allows you to not do any synchronization, right? And then from there, once a response arrives, you take your callback and then you feed it into the callback. So the whole thing basically is non-blocking, because your threads could wait on the callback, And then the event loops also, they don't care, right? They look at the NIO selectors, and if anything is ready to read, they read it and then pass it up the pipeline.
But from my understanding, the difference between async and non-logging is that with async or with non-logging, you have this event loop where you get a notification that your data is ready to be read from the operating system into your sort of application memory space.
Okay.
Whereas with async, you get a notification that now your data has been read into your application. So I'm wondering if it's real async. Those buffers that we're talking about, is that really is that some memory that's been populated by the operating system, or has there been some copy involved where the CPU is reading?
So, okay, so I think the semantics of async and non-blocking, I think it's very blurry. But to answer your question, so how the byte buffer gets into NIO, that's part of the JVM, right? So Netty doesn't care about in that regard if you use the NIO transport. If you use the ePOL transport, it is using edge triggered ePOL. So it's basically running the event loops, and then it's asking ePOL proactively, do you have anything for me, right? Instead of basically blocking on a selector and saying, wake me up when there is anything for me, right? So there's a difference with NIO. You need to block on the, I mean, you don't have to block on the selector, but it's very common, right? So you block on the selector, and then the JVM will wake your thread up until there is something to read from NIO. You can always call select now, but now we're going very deep into how NIO works, right? But you can also call select now, and then you have your own backup mechanism. So that's actually one thing, but it's a little more advanced. So one thing that we built with Netty is that if you have a client, as long as you're in the event loops, there is no cost in writing and so forth, because you're running in the same event loops. But if you're writing from outside into the event loop and you do a write and flush, basically what you need to do is you need to wake up the selector, which is a syscall. So going from outside inside is more costly than staying inside. So what we did in recent versions is we added more flexibility, because previously Netty would block on the selector and then you would wake it up, right? So you would have a syscall. Now, what we added is you can define custom backup strategies, like with log, pack support, nanos, and so forth, right? So you can trade CPU for not doing those syscalls. So for example, let's say you could spin for a specific amount of time, and when you're writing from outside inside, it would not wake up the selector because it would consume the queue proactively, and only if the time is over, because you don't want to spin forever, so that would you clog your CPUs, right? Then you would block on the selector.
I think we'll have to cut it here.
Okay, we can definitely discuss afterwards. Thanks very much.